Good morning, Desire.
Good morning, Dr. Duro.
Good morning. How's work?
Good morning, sir.
Good morning. Good morning, everybody.
God bless you, sir.
God bless you. Welcome. We are having how many people do we have? 6. So I think we just wait for a few minutes. We have 6 participants now. Let's just wait for a few minutes, 1 or 2 minutes, so that we start. Okay, yes, let's start today's business. Today we'll be discussing probability and normal distribution. Probability and normal distribution. You remember the last series of sessions we've had, we talked about statistics being divided into descriptive and inferential statistics. And in between both of them, we have the probability. Probability is the link between descriptive and inferential statistics. And actually, probability is in the heart of statistics. Let me just put the annotation. Yeah. You can see the maxim. My maxim here, statistical thinking starts with probability and ends with probability. You can hear me now. If you can hear me, just raise your hand. Many people you are hiding yourself. If you can hear me, can you hear me? If somebody can hear me, can just talk. Unmute
I can
yourself.
hear.
Okay, that's great. Okay, thank you.
I can hear you, sir.
I can hear you well.
Okay, thank you. Let me just start. Yeah, I was a disconnection here. Let me just start. Okay. Annotation. Yes. Yes. You can see the maxim, statistic. Okay, raise hand. 2 people raise hand. Okay, you can see. Okay, Aisha Bello. Okay, that's great. That's great. Let's just start. Statistical thinking starts with probability and hence probability. You know, the other time we talk about descriptive statistics and inferential statistics, say the link between the descriptive and inferential statistics is probability. And we've discussed descriptive statistics. Today we'll be looking at probability, maybe today and Thursday. By next week, we'll talk about inferential statistics. What is probability? No, it's a language that many people are familiar with. Even uneducated person probably use the word probably. But it's at the heart of statistics, and it's not as easy to conceptualize as people think. But for the everyday usage, well, the chance of an event occurring, anybody can define that. But though when you study it very well, you see that you can quantify probability. Before you can make much sense of probability, you need to quantify. So it's a measure of the chance of a given event occurring. We all know that it lies in the heart of statistical theory because it forms the basis of differential statistics. That was what I told you, that before we could proceed with differential statistics, you must unravel the mystery behind probability. It has its origin in the games of chance, such as dice and card game. You know, the origin, the people that first used statistics were people that were gambling. So it may surprise you to hear that. It's true that the statistic probability developed, and it has contributed much, or so much, to the subject of statistics. Possible values of probability. Number one, it is a positive number that lies between 0 and 1 inclusive. That shows that probability can be 0, it can be 1. A lot of the value may lie between 0 and 1. Very soon, by the time we get to special statistics, you realize that the p-value you hear of is actually, that p is probability. That's the meaning of p. It's actually probability value. So that is why you cannot talk about inferential statistics without probability. And that's why I don't even like discussing sample size determination without treating probability and inferential statistics. It is after you understand these two areas that you will be able to understand sample size determination. That is why the commonest reason people contact statisticians is sample size determination. It looks simple, but it's also simple. It is when you want to do, your study, especially when it involves examination. If it is just to write paper, and if somebody rejects your paper, refuse to publish it, you can go to another place. But when it comes to examination, PhD thesis, master thesis, fellowship thesis, is a serious business. That is when people call statistician, I'm having issue with sample size determination. You realize, you know that when some people say p-value cannot be 0, it can be 0 because it's probability. Probability, the value ranges between, possible value range between 0 and 1, inclusive of 0 and 1. If it is 0, the event cannot occur. If it is 1, the occurrence of the event is certain. We all know that It can be expressed as a decimal such as 0.2, 0.5, 0.8. Just give an example. Because it's between 0 and 1, it cannot be more than 1, it cannot be less than 0. It may be given as fraction also. If you say 2 over 10, that is 0.2. 1 over 2, that is 0.5. 80 over 100, that is 0.8. So that 0.8 is like 80%. 0.5 is 50%. 0.2 is 20%. So you get to understand that you express, if you express something as decimal, if you want to express it as percentage, just multiply it by 100. If something is expressed as 100, you want to express as decimal, divide by 100. So 100% and 1 means the same thing. Then the probability of the complementary event not occurring, we'll talk about that later when we reach rules of probability. The probability of the complementary event means event not occurring. If I say the probability of me going to work today is 0.2, that the complementary event is me not going to work. And the probability that shows that it will be 1 minus 0.2, which is 0.8. So that's why here it is stated that the probability of the complementary event, that is event not occurring, is 1 minus the probability of the event occurring. Now, that's just a preamble. Let's quickly look at the approaches to probability. Because this, like I said at the inception, everybody use the word probability. Even the woman that is selling granite in the front of your hospital or of your office, if they realize that, oh, it's as if it will rain today, you say, probably it's going to rain. The probability of it raining today is very high. She pack her things and leave. If other people are packing and somebody realizes, I don't think it will rain. The way the probability is low. The person may still stay. So you see the way it guides them. So there are different approaches. So you discover that you have the qualitative approach and quantitative approach. Now, the first one is subjective approach. Subjective approach, that is, you can divide into two, subjective approach or objective approach. What is subjective approach? When you say something is subjective, it actually means that no evidence. When we say something is subjective, it's more qualitative. No, well, don't let me say qualitative, because when you say qualitative and I say no evidence, especially people that get involved in qualitative research, and say, what do you mean? So it means that subjective means that there's no evidence. You know, when you say something is subjective, like if it's something that nobody else can verify. If I just saying something based on my own feeling, there's no way you can verify it's subjective. But if it is something that is not, it is objective, you can verify. If I say this is the way I arrive at the answer, you can verify that particular thing is objective. Now, subjective approach is when people, if I ask you, some of you, okay, if your friend, a European friend is coming to Nigeria, or to, he has not come to Africa before, and he's now asking you, what is the probability of that person having malaria if he doesn't take preventive measure? What will you say? If I ask many people, will give different answers. Some people will say 50-50. Some people will say the probability is high that he will have malaria. Some people will even say it's 70%. Some people will say 80%. All of them is still subjective in the sense that they're just talking based on their own perception. Though some people may be saying it based on experience, but still there's no objectivity there because they are not presenting evidence. Even the person that says based on experience, another person can based on experience and give different value also. That is subjective approach to probability because there's no evidence. The objective approach, where there is evidence, we have the classical approach and the relative frequency approach. The relative frequency approach, as the name, well, let me just say classical approach first. The classical approach, the difference between the classical and the relative frequency approach is the classical approach is based on some setting. There is an established setting, or there are some established setting. For example, if you toss a coin, what is the probability that it will be heard? Because there is the setting, you have not touched the frame, because probability is actually predict something that will happen in the future. Probability is about the future. Now, I have not tossed the coin, but I'm now asking, if you toss the coin, what's the probability that it's going to be heard? But because you already know that this coin has two sides, head or tail. So if it's two sides, so it's 50-50. Half of the time, it will be you, probably it will be head. Half of the time, it will be tail. So you can see in that setting, there's an established setting because the coin has two faces. If you toss a die has 6 faces. What's the on each face 1, 2, 3 to 6. What's the probability of 3? It's 1 out of the 6 that give you 3. What's the probability of 5? It's 1 out of the 5. So the probability of 3 now is, you can also, oh, because there's a setting. You say the probability of 3 is 1 out of 6. The same thing with all those other numbers. This probability of something like tossing coin or tossing die is classical approach. You know, it's scientific, there's evidence. It's not like the one that there's no evidence. There's evidence. But it's classical approach in the sense that there's an established setting. Even though you have not done, you have basis for prediction, because there's an established. Classical means established, something that's already established. That is classical. That is what we call classical approach. Another name for that classical approach is priori. Priori means that there's a prior knowledge of the setting. Priori approach. Now, let's talk about relative frequency approach. The relative frequency approach is if you remember the last lecture, when we talk about frequency distribution, you know, the different type of distribution. We talk about 4 different types: frequency distribution, relative frequency distribution, cumulative frequency distribution, and cumulative relative frequency distribution. That word relative is what I want you to remember. Relative frequency. I say it is when you standardize, you put it at percentage. And from what we discussed, it is obvious that almost all our results, when we put them on the frequency table, we show the percentage. That is relative frequency. What relative frequency approach just means that, for example, if you apply the principle to your friend, European friend that is coming, that is asking you, if the person doesn't take preventive measure, what's the probability of the person having malaria? You know, if a study has been done by maybe one researcher, you can go, Professor so and so, at all. I've found in their study in Nigeria, they found out that 80% of the Europeans without preventive measure develop malaria. You know, you are quoting the work that has been done before, and that is relative frequency approach. You can remember now. So it's what is like you are looking at the former frequency table, the what have been done before. Look at the frequency table and say, okay, this is the frequency. There's an evidence. If you look at it, both classical approach and relative frequency approach, there are evidence. You have evidence, but the evidence differ. In classical approach, is just the setting you look at. But the relative frequency approach, what can be done? You are looking at the past, what has been done before. Similar thing, the similar event, how it happened before. What is the probability? What was the probability you are quoting? That is why you quote recent work, believing that what happened recently, 1 year, 2 years, 3 or 4 years ago, can still happen now. That is why when work is old, people don't want to believe because it is already old. If you are quoting what that was done 20 years ago, it's a look for recent literature. It is believed, though it's still relative frequency, but this thing is too far. So what happened 30 years ago may not happen now. But those ones that are recent, you believe that they may still happen. That's why you are quoting them. Otherwise, you will not quote, because something has happened before doesn't mean that the same thing will happen. It's just a prediction.
Sorry, sir, I can't hear you again. I didn't know whether it's my network or your network.
So I've unmuted myself. Sorry, there was a problem with the network. Whenever it happens like that, you can hear now. I've unmuted myself. Whenever it happens like that, it goes off. Sorry, I don't know what's happening. Let's continue. Where is this slide? Okay. Yes, sorry for that. Yes. So that is relative frequency approach. I think we will discuss much about that. Now, let us look, how do you calculate? How do you quantify? No, the quantification comes for the objective approaches. That is the classical approach and relative frequency approach. You cannot calculate something that has no evidence. Subjective approach. There's not, if anybody give figure, just give figure offhand. But for classical approach and relative frequency approach, which are the two objective approaches, the calculation differ, the formula differ. It's very simple. There's no big thing about it. What it does mean is that look at the definition of classical approach. Probability that an event happen or occur is number of outcomes favorable to the event divided by the number of possible outcomes. For example I give about classical approach, die and coin. If you toss a coin, what is the possible outcome? Number of possible outcome is 2, head or tail, 2. So probability, an event is probability that head is 1 out of the 2. Very simple. So 1 divided by 2. Number of outcome favorable to head is 1. Number of possible outcome, 2. If it is a die, you are tossing 6 side. Total number of possible outcomes 6. 1, 2, 3, 4, up to 6. Then the probability that is 4 is 1 out of the 6. So it will be number of outcome favorable to the event, which is 1 over 6. That's very simple for classical approach. For example, now let's quickly look at the example of classical approach. List and discuss. I want you to just brainstorm. Let me just give you 1 minute. List and discuss all the possible outcomes of tossing 1 coin. How many possible outcomes? Tossing 2 coins. How many possible outcomes? Tossing 1 die. How many possible outcomes? 2 dies. How many possible outcomes? So that we don't waste our time. I just move and reflect. Of course, tossing 1 coin, when you flip, either you flip or toss, it's the same thing. When you toss 1 coin, it's either head or tail. So you have 2 possible outcomes. So we talk about calculation before. We've already said that the first one is half, that one is half. Then if you toss 2 coin rather, how many possible outcomes? You have 4 possible outcomes. It's either is head, tail. Look at it. Let's say the first coin is red. In the head, sorry, the head is, you just assume that, okay, you toss the coin 2 times. Tossing 2 coin or tossing coin 2 times mean the same thing. Okay, the head is designated as red, the tail, and you see blue here. Now, the first one, if it is the first one is head, the second one, the first one is tail, is the blue. So now, this, if the first one is head and the second one is head, it will be head. If the first one is head and second one is tail, that's head tail. If this first one is tail and second one is head, that is tail head. The first one is tail and the second one is tail. So we have 4 possible outcomes. You can calculate their probability because head tail TL mean the same thing. One is head, one is tail. Can you see? If you look at it, if you want to now calculate, okay, you now say, okay, 2 head, 1 tail. Okay, sorry, this column is number of head. Here is 2. Number of head here, 1. Number of head is 1. There's no head here. But the issue there is that we have one answer is head, 2 of them head tail, and 1 of them tail. So if you look at it, each of them, if you look at it, that is head is 0.25. That is half multiplied by half. 0.5 multiplied by 0.5. We talk about how the calculation is, but just know it's very simple. We have 4 possible outcomes. All of them have equal probability, and they must add up to 1. So it's 0.25, 0.25. That is 1 over 4, 1 over 4, 1 over 4, 1 over 4. Those are the possible outcomes of tossing 2 coins. Let's go to die. Tossing 1 die. The possible outcomes, of course, we know it's 6. Either 1, 2, 3, 4, 5, 6. Now, the one that is not as simple as you think is tossing 2 die. Some 2 dice rather. Some people say that when you ask them, they say that is how many possible outcomes? They say 12. It's actually, if you look at it, it's actually 36, because if you look at this, let's say the first die is red, the other one is green. You will see that even when one is red, you can couple with 1 of green, 2 of green, 3 of green, 4 of green, 5 of green, 6 of green. So 1 with any of these one, those are 6 outcomes, possible outcomes. So when you pick it for each of the remaining 5, all of them will have 6, 6, 6, 6, 6 times 6, making 36. So there are 36 possible outcomes tossing 2 die. And this outcome, you can actually look at it. Okay, let's just leave that one because there are some complex things, because we don't have much time to discuss. But if you read the module, which I'm going to send to you, you're going to get it on the site, my website, the module. You'll be able to understand better. Let's just proceed. Let's go to the calculation of relative frequency. The relative frequency approach, very simple. The way you calculate, you form your frequency table. Number of time event occur in the past divided by total number of observation. Total number of observation is your sample size in your study. So in the past, what the study that have been done in the past, what was the sample size? That's the total number of observation. Then the total number of events that occur. Like for example now, if the issue of European people, if 200, you study 200 Europeans that came to Africa or to Nigeria, the sample size is 200. How many develop malaria? Maybe 80. So the probability of developing malaria will be 80 over 200, which is 40%. If there are 160 people that develop malaria among them, that will be 80%. 160 over 200. Simple. Look at an exercise here. The National Center for Health Statistics reported that every 1,000 deaths, 81 result from road traffic accident, 55 from cancer, 156 from heart disease, 367 from infectious disease, 22 from childbirth, and 319 from other causes. Estimate the probability that a particular death is caused by heart disease. All you need to do is, okay, the total number is 1,000. That is the sample size, number of deaths. Then divide 156, because they say what's the probability that is due to the death is due to heart disease. 156 over 1,000. That is, what's the percentage? That's 50.6%. Simple. They'll be saying that how can you say sample size of 100 deaths? You know, when we're talking about population the other time, I said there is statistical population and there is popular population. So when you are studying cases, record or case note, that is statistical population. This one is the record they look at, record of the death, the cause of the death. So the populations there you sample is statistical population. But when you are sample the real people, that is popular population. They still mean the same thing in statistics. Now, before we proceed to some rules and look at some issues, deeper issues, let's look at some language terms frequently used for calculating probability. You hear this word like experiment. What does it mean? Experiment here is different from the experiment in the laboratory. It's different from experiment, which is a study design, even in research. Because experiment in laboratory is different from the experiment as study design. And it's different from experiment in probability. Trial, outcome, event, those are languages you see, you hear of rather. Now, let's start with experiment. What does it mean? It's the process of data collection. It's very simple. By tossing a die, the process of tossing a die and looking at your outcome is experiment. If you go to the field, by asking a question, oh, what is your ethnicity? No, ethnicity is a variable. By asking the ethnicity and the person, you elicit response from that person, say, oh, I'm Igbo. And you now document it. That you have performed an experiment. That is observation. If you say, okay, stand on the weighing scale, you measure this, you record the weight, that is an experiment. By the time you look at maybe part of your sample, your data collection is to look at pallor. In every side, you check pallor or no pallor. It's an experiment. When you measure the hemoglobin concentration, one person, even though in the laboratory is experimented, in statistics, in probability, the experiment is different. In the sense that you have captured this person hemoglobin concentration is the experiment. It's not the one they do in the laboratory that they run the test. No, but that you capture, either you go to the lab or they supply you the information from the lab or anywhere that the hemoglobin concentration is so and so. That is an experiment. So observation, that is collecting data, that is experiment. You know, if you toss a coin 100 times, the sample size for is 100. Each of the tossing is an experiment. So when you have each of the observation you make, data for each variable is an experiment. So experiment encompasses you eliciting response. You get the value and record it. That is experiment. Now, trial is a particular art of experiment. Now, if I ask for what is your ethnicity, you told me, I recorded it. I asked another person, told me, I recorded it. That's two trial on that experiment, because the experiment here is eliciting response for ethnicity. If I ask it from 100 people, I perform 100 experiments on the knowing ethnicity. Of course, when you go to, you administer your questionnaire, you don't just go and finish for each variable, and begin to go to 100, 1,000 people for each variable and now come back. No, in each, as somebody is attending to you, you ask for all the variables. But what I'm telling you that for each of the variable, for the first person you interview, for each of those, maybe you have 30 variables in your questionnaire, you have performed the first experiment for each of the variable. When you move to the next person, that's you are performing. So one experiment completed is one trial. When you have done it for 5 people, that is 5 trial. So if you toss a coin 5 times, that's 5 trial. I think that's very simple. Now, you can now see the difference between experiment and trial. So trial is the particular art of an experiment. Now let's look at outcome. Outcome is the result of a particular trial. Like if you toss a coin, you're performing an experiment, the first that you are, as you perform the experiment, the result is head. Or if it's 2 coins you toss, the result is head or head tail. That is the outcome. It's outcome. You're like somebody that gave birth. It's an outcome. So when it's just like okay, when I asked you, what is your ethnicity? You told me that value. You told is the outcome. If I measure your, I say what is your weight, or I measure your weight, and I say you are 87 or 90, is an outcome. I also measure your every other variable. We have outcome like height, 1.65 is an outcome. Now, event is the particular outcome of experience defined by a given rule. Now, if I want to know your, I ask for your weight, I ask for your height. These are outcome, each of them. Then I say, okay, I want to, and I calculate, and I say, oh, you are overweight or obese. It's an event that you are obese. Okay, let me use another example. I measure your hemoglobin, okay, or I measure your blood pressure. I measure your systolic blood pressure. Your systolic blood pressure, by measuring it, it's an art of an experiment and getting results. By measuring it once from one person is a trial. The result I get from that trial of that experiment is the systolic blood pressure is 150 millimeters of mercury. That you are hypertensive because I've applied the rule that any systolic blood pressure that is greater than 140 is hypertension. So the person is hypertensive. By applying that rule that you are hypertensive is an event. I think it's very straightforward now. How experiment, trial, outcome, event are related. Let's proceed. Now, there's something, when you talk about probability, we use Venn diagram. The reason is very simple, is to be able to conceptualize, to be able to see, have a mental picture, because as I've said from the inception, the first series of the lecture, I said that statistics is what happens in everyday life, but which is modeling what happens in everyday life. You either model through diagram or picture, or through equation, or through graph, or through table. You must just use something to show. So Venn diagram is to model the way statistics work in the real life. Now, it's a pictorial method used to show the relationship between different set or group of objects. It's in probability theory, this set can be used to represent events. So here we are using the set of objects to represent event. For example, now, if you say event A, event A may oh, I toss the first coin. Event B, I toss the second one. Okay, the event is not I told the first one is head. I told the second one is tail or is head also. Or I toss a die. It give me, the event may be, oh, I toss a die, it give me odd number. I toss the second one. The probability that it give me number that is greater than 3. Can you see now? So you see, the event is usually defined by rule. I toss a die, it gives me odd number. Tossing a die will give you outcome, but that it gives me odd number is an event because I have applied a rule to filter, to expect what I'm expecting, a particular type of result. It's just like examination. You write jam, the person that write jam is called, they say the person is called 250. Oh, say that is the outcome. But it's admitted, it's an article, it's an event. If it's not admitted, it's an event also. So they use a cutoff point to do the admission. Now, it's the same thing here. Now, what I don't want to talk much because when we are still going to the rule for you to conceptualize very well, but what I want you to see what the Venn diagram does. Now, what it does is that when you have two objects or probability or event like that, sometimes they may overlap. Overlap in the sense that they may not overlap, they may be separate. If there are some things that are common among them, there is an overlap. Like for example that I gave, if A is tossing a coin, tossing a die, giving me odd number. Odd number there are 1, 5, 3, and 5. And I say another number greater than 3. The second one is giving me number greater than 3. The one that are greater than 3 are 4, 5, and 6. You can see the common thing among the two is 5. 5 is odd number, is in the first event. 5 is greater than 4, is in the second event. So this area, if you look at the first diagram now, this area that is painted is the common between them. That is the intersection. So you will now see that for the first one, 1 and 5, 1 and 3 rather, would be here within the A, but it's not within the painted area. Then 4 and 6 will be within this B, but it's not in the painted area. That is the way it works. Now, that is why event A and B, that is, this one is showing something that happened in A and also happened in B. That is the painted area. But if I just say that, okay, what is the probability if I now say A or B? That is, the A is odd number. Event B greater than 4, greater than 3. Everyone is captured because if I now say or, it gave me odd number or number greater than 4. You will see that, well, okay, let's say, sorry, the number greater than maybe 2, something like that. Or, but, okay, that one will not work here because here is talking of everything, A or B, everything together. A, well, is the same thing. Is A or B, everything together. Now, let's look at this one. Event, if you remember the first slide, I talk about complement, probability of a complement event, of an event. If I say probability of me going to work is A, the complement of A is probability of me not going to work. That's what they are showing here. Everything, you know, if you look at those things like circle, they are within the box. The box is the universal. In our case now, in the case of the one I just gave now, 2 will be outside because if you look at when I say probability of odd number 1, 3, 5, greater than 3, 4, 5, 6. It's only 2 that is not captured. 2 will be outside each of them, but we're still within the box because that's the universal, the total. Because if you all the possible outcome are 1, 2, up to 5. So 2 is not captured in A, it's not captured in B, it will be outside. So, but when we are talking of complement, anything that is not A is the complement. That is why you see all this shaded area is the complement of A. This can be combined when you combine probability A and not B. If you look at it, A not B. Can you see now? Probability for A but not B. For example, the example I gave now, probability that is odd number but not greater than, because B is greater than 3, not greater than 3. Can you see? It will only be 1 and 2, odd number. That's the one within the box here, 1 and 2. One number, but not greater than, not B, not greater than 3. Now, let's look at Venn diagram also in the more quantitative way. For example, consider the different possible outcome of rolling a die. Okay, like what I said. Okay. The first one is rolling an odd number 1, 3, 5. The second one, rolling a multiple of 3. This one is different from what I said the other time. 3. Multiple of 3 are 3 and 6. That is multiple of 3. Something you can, 3 is there, then 6. Can you see now? The possible outcome are 1, 2, 3, 4, 5, 6. The one rolling number that is 1, 2, 3, that is odd number, that is 1, 2, 3, A, within A circle. Or multiple of 3 within C circle. The intersection, the one that is common to both of them is 3. Then the one that is all the other possible outcomes that are out of those 3 and 3 are outside, 2 and 4. Now you can see. Now let's give, if we say, okay, what is probability that is A, that is odd number and also multiple of 3. It's only 1, it's only 3 that's also. But if you say it's A or you are adding 1, 5, 3, 6 together, that is at least it can be any of them. That is A or B. That is multiple odd number or multiple of 3. So 1, 5, 3, 6. That's the way it works. When we get to the rules of probability, we are going there now. You understand better. Look at this other Venn diagram also. A person is selected randomly. Probability that AFL is 10. Look at it. A person is selected at random. This A, this B. The probability that is A, 8 plus 2, that's 10. The total, if you look at the total, is 20. A plus 2 plus 4, 12 plus 6, 20. If you look, the total number of students is 20. Take like AFL, A, 6 like baseball, and 2 like boat. Can you see now? So 10 like AFL, A is 10. The probability if select somebody is 10, 10 out of the 20 is A, is 10 out of the 20. The probability that is A, that is AFL or baseball, or you just add A plus 2 plus 4. You're going to see why we don't count. If you look at it, the people that are baseball, 6. People that are AFL, 10. But if you go and add 8, 2, and 10 and 6, it will give you 16. You will have counted those ones that have both. You will have double counted. And that is why you don't do that. You just look at this diagram. 8 plus 2 plus 4, it gives you 14. 14 out of 20. But that is both AFL and baseball. That is the person that play both is only 2 out of 20. Can you see? Don't like AFL and baseball. Do not like. If you look at it, it's only 2 that like both. Do not like. So the complement of that one, that is, you remove it from the 20. That's 80 over 20. So the logic, as you go on, it will click more. Now, let's quickly talk about the rules, how it works. This probability, you see, is very, very important. You need to understand the logic very well because you use it in many areas of life. We're going to see how you use to search in search engine. We're going to talk about how it's used to analyze. When you are, using computer to do your analysis, you use this logic here. Now, rules of probability. Related time, before we go to the rule, what are the related time? You'll be hearing something like independent event, dependent event. 2 events that occur in the sequence. If the outcome of any event does not affect the possible outcome of the other event, then the events are independent. For example, if I'm asking, probability that your child, you bring a child to the clinic, the probability that the child has fever is an event. Probability that the child has vomited is an event. But both of them, they are not For the fact that the child vomited does not preclude the child from having fever. They are independent. Now, that is example of independent. You're like, oh, probably you are an outside person, and probably you are a doctor. They are independent. You can be an outside person and be a doctor. So, probability of outside ethnicity and probability of being a doctor as a participant in this program, they are independent. Now, dependent event, 2 or more events that occur in a sequence, if the outcome of any event changes the possible outcome of the other event, then the events are dependent. There are some events that are dependent. Now, if maybe you choose, you say that you are picking a particular class. Or in a particular, well, is it class or hospital? Is it the probability of choosing a doctor to be part of the COVID-19 part of we have 20 doctors, and you have 20 no, we have 20 staff in that hospital, and they want to choose, if they want to choose one person or they want to choose 2 person, the probability of choosing the first person and 20 staff, 2 doctors there, 20 staff out of which we have 2 doctors. They just want to choose one person. The probability of that person, the first one being a doctor, is 2/20. If they are choosing the second one, the probability of choosing the person being a doctor is 1/19, because they have chosen the first one. The first one has affected the 2 events are not independent. Because once you choose the doctor, the person that have been chosen before, it cannot be part of the person they want to choose again. It has affected the total, also affected the number of doctors there. So can you see those 2 events? The probability of the person, the first person being a doctor, and the probability of the first person being a doctor, they are dependent. Even the probability of second person being a nurse, if they have 6 nurses out of the 20, they are still dependent, because by the time you remove nurses, 1 doctor, the number of staff remaining is 19. So 6 out of 19. So you see, the 2 events are dependent. I just give that example for us to be able to conceptualize. Let's see, look, because I prefer using live example than using this A is there just to denote A. Because sometimes when you say A, probability of A is equal to this, people just say, what is A, what is B? But actually, they just use A to represent an event. Like the one I just gave, the probability of the first one be a doctor is an event. The probability of the second one being a nurse is an event. The 2 events are dependent. Now, let's look at mutually exclusive events. The mutually exclusive event is event that if one particular event happen, the other one cannot happen. To 2 events, there is no overlap. When they say mutually exclusive, there's no overlap. For example, if we said, okay, the probability of, in this study, in this what do I call it, in this training we are doing, in this lecture, the probability of a person being a doctor and the probability of another person being a nurse. Here now we are not choosing, it just being. They are not dependent, they are mutually exclusive. They are mutually exclusive. Now, mutually exclusive event, there's no overlap. Let me give another example. If you are a male, you cannot be a female at the same time. These are mutually exclusive. But as the example I gave about a child, okay, a child being a male, your child being a male and being a female, they are mutually exclusive. If a child is a male, it cannot be a female. But if a child have fever, it can still have weight loss or vomiting. They are not mutually exclusive. Now you may be saying something, okay, this mutually, can we say that when something is mutually exclusive, it's independent? Yes. Or when something is not mutually exclusive, it's independent. All independent events, they are not mutually exclusive. Independent events cannot be mutually exclusive. Mutually exclusive events, they are all dependent, but not all dependent are mutually exclusive. Not all dependent, we're going to see it later, not all dependent are mutually exclusive. So that is why sometimes it's difficult to show dependent and independent with Venn diagram. But it's easy for mutually exclusive and non mutually exclusive. Because all mutually exclusive are dependent, but not all dependent are mutually exclusive. So you can draw something can be dependent, and these two diagrams work for it. It can be dependent and non mutually exclusive. It can be dependent and mutually exclusive. But if it is independent, it cannot be mutually exclusive. So independent cannot look like this. But dependent can look like both of these diagrams, mutually exclusive or non mutually exclusive. But independent can only look at this overlap. It cannot look like the one where there's no overlap. I think we'll proceed. Another example for you to conceptualize independent and mutually exclusive. Look at independent event. It rain, I win lottery. Both of them has nothing to do with, even though they can happen at the same time. But it's not because they don't influence one another. So they are independent events. Winning lottery does not prevent rain, and rain does not prevent you from winning lottery. Well, you may say it prevents if you don't go there and play the lottery because of the rain disturbing you. Now, mutually exclusive event, I flip heads, so I cannot flip tail. And you see that it's mutually. If you say, okay, as you flip one coin, it says head. If it's head, it cannot be tail. And if it's tail, it cannot be head. Because they are mutually exclusive. You remember this word when we're talking about displaying frequency distribution with graph. We say the pie chart, but pie chart can only be used for mutually exclusive. So when we talk about event, we are talking of variable. You know, this event talking about variable. It's just logic. You know, I said that, okay, when I'm collecting data, I say, oh, I want to know, do I know need to ask, unless if you dress somehow, or unless if I'm looking for gender. No, gender is different from sex. If I want to collect, I'm administering questionnaire to you. I will not be asking you if you sex I'm interested in, and say, since I can see you, I just think that you are male or female. But if it is gender, because some people are female, they are lesbian. This female is a husband to another person. So in that sense, it's a male gender. Or you can see a man, you think it's a male. But he's homosexual, he's a wife to somebody. So the person may be a female. That is when you are considering gender. But if I'm just looking at sex, okay, for the fact that you are a male is an event. So be a female and be a male, both of them are events that are mutually exclusive. They cannot overlap. But for the fact that I say, oh, do you have fever? Does not preclude you from having weight loss. They are independent events. They are not mutually exclusive. I think we proceed. Complementary probabilities, I think I've talked about it in the other one. There are two of them anyway. The complementary probability, whenever I look at complement of A, when you look at the whole universe, this box you are seeing is the possible outcome for that probability. If let's say we are talking of tossing a die, or a die, yes, we have 6 possible outcomes, 1, 2, up to 6, 1, 2, 3, 4, 5, 6. If my event is probability of having multiple of 3, like I said the other time, which is 3 and 6. Multiple of 3 will be this A. Complement of A would be anything outside that multiple of 3, which is 1, 2, 4, 5. That's complement of A. Now, in that situation now, there's a situation where say there are 2 possible outcomes. Okay, complement of A, that is in these 2 possible outcomes now, we're talking of multiple of 3 or non-multiple of 3. So that's just it. When you have 2 possible outcomes, the first one will be the event, the complement, the second outcome is the complement to the other one. That's the logic in binomial distribution. We are going to talk about it later. When male or female. Sex, male is a complement of female, female is complement of male. Okay, don't let us waste time. But when you look at least, that first example is when you are having 2 possible outcomes. But you may have many outcomes, like tossing a coin, which you are 1, 2, 3, tossing die, 1 to 6 possible outcome. I may say, okay, if I say at least 1, I've dichotomized it. It's the same thing, complement. At least 1. The at least 1 will be just 1. At least 2 will be 2 or 1. The complement of at least 2 will be 3, 4, 5, 6. No, sorry, I don't. At least 2 is 2, 3, 4, 5, 6. The complement is 1. If I say at most 2, that will be 2 and 1. The complement of at most 2 will be 3, 4, 5, 6. So that's where, this complement is just talking about binomial distribution. Either there are 2 possible outcomes. Now, addition rule. Let's look at addition rule. In the later part of the slide, there are about 10 rules. Why I don't want to bring, because there's no point bringing rules first. There are some rules you don't do. Some of them I've talked about it even at the inception. I want the 10 rules you're going to see now is like a summary you're going to give. But let's just quickly look at how do we add. For addition rule, we have this general additional rule, which is this one for non-mutually exclusive. We now have addition rule for mutually exclusive. Look at it. Non-mutual, let's look at this diagram below for the general addition rule, which is A or B, because in addition is all you are using. If you remember the other time, if you want to get it all, add everything, you say, what's the probability A or B? That is, what's the probability that when I toss the die, the value is odd number or complement of 3. You are adding multiple of 3. You are adding the 2 because A is odd number. Even A is odd number, even B is a multiple of 3. So when you want to say A or B, you are adding them. If you look at, you are adding either of them. A, you add everything together. That is why the addition rule go with or. Can you see A or B? That is, if you look at it, A alone is the shaded area here. B alone is the shaded area here. But if you look at it, if you go and be adding them like that, you will likely double count this intersection there. Can you see? So when you now overlap them, you now say you now count A, whatever is here, whatever is here, whatever are now add together. So whatever is in the box, one part of A, and whatever is in the green part, plus whatever is in the white part of B, that will be the addition. Rather than do it separately, because the intersection, this place is counted twice. But when you put it together, so that is why you say A, this is A and B, rather. This is A and B, this is A, this is B, this is A and B. So you now add A. That is why the probability addition rule for probability is probability A plus probability B minus probability A and B. So why you minus is that it has counted 2 times. When you add A and B, this A and B has appeared 2 times. So you remove one of them. That is why I say minus probability A and B. That is A and B, it is intersection. So the addition rule for probability is probability A. When we say probability A or B is probability A plus probability B minus probability A and B. If we use the example of what we do, the A is odd number. That is 135. The B is multiple of 3, 36. Can you see 3? So if you now say the probability of odd number would be 134. That is 3. That is the value of 135. That's 3 out of 6. 3 over 6. The probability of the multiple of 3 will be 3 and 6, which is 2 over 6. If you go and add 3 over 6 and 2 over 6, that 3, which appear as odd and also appear as a multiple of 3, are contributed 2 times. That's why you need to remove its probability. So the probability of having 3 will be 1 over 6. So in that case now, it has to be 3 over 6, which is probability of odd, plus 2 over 6, which is probability of multiple of 3, minus probability of 3, which is 1 over 3. Because 3 is the intersection, it's the A or B, A and B. Very simple. Now, for mutually exclusive, there is no intersection. That my A and B is 0. So if A and B, this last section of the formula is 0, so it will just be probability A plus probability B. If let's say there's no overlap, then if let's say the answer, maybe the event, if let's say the event B, instead of saying the multiple of 3 is even number that is greater than 3. If we say even number that is greater than 3, that will be 4 and 6. If you look at it, 4 and 6 did not appear in the other, so there's no overlap. The other one is odd number 135. The other one is 4 and 6. So you can add them together without removing them. That is this mutually exclusive. Whenever there's no overlap, one probability has nothing to do with the other probability, you just add them together. But if there's overlap, they are not mutually exclusive. You need to remove the value of the overlap because the value of overlap have been counted 2 times. I think that's for addition rule. Multiplication rule. Rules of probability, multiplication rule. It is for probability of simultaneous occurrence of 2 events like A and B. When you see the word A and B, that's so A and B. Normally, that one also have what we call general rule, the general probability. But just we'll talk about that when we get to the rule because I listed the rule. But just look at this one here, this is the example here. A and B just probability A multiplied by probability B. If the other one say A and B, what is the probability that is odd number and multiple of it? So we already said it's 3. The one that is odd number and multiple is the one that's common to them, which is the 3. So if we multiply, what is the probability that is the odd number, which is 3 over 6, which is half. Probability that is, the other one is 2 over 6. If you multiply, it will still give you that number 1 over 6. Now, let's look at what we call conditional probability. This conditional probability is not far from the multiplication aspect. Probability of occurrence of an event that another event has occurred. If you are looking at probability of occurrence of an event, provided another event has occurred. It's very simple. That is, probability of B, this way it is written. Probability of A provided B has happened. Probability of A provided B has happened. Now, is probability of A and B, which is, whenever I say A and B, which is, you remember the multiplication rule, the intersection, divided by the probability of B, because the B has happened. Look at it. So what is just there is that B has happened. It's only those one that B has happened to that will form the denominator. That's what he's telling you. It's just like say, okay, what is the probability of diabetes among the people that are obese? You did your study. We have people that are obese. We have people that are diabetic. You now say, among the people that are obese, what's the probability of? So that is, you are talking of probability of diabetes, provided the person is obese. So the B here is the obesity. So you now, in your analysis, you only select the people that are obese. I now put among the people that are obese. Can you see people that is the intersection of the obesity? This is the A is the diabetes, B is obesity. So intersection of the obesity is the people that are obese that are diabetic. That's the intersection over the people that are obese. Obese is the condition. So if you look at that logic, it's very simple. You're able to marry it, because if you don't get the logic like that, it's just an equation, just be writing A and B. You know, I've already told you, probability statistic is representing life situation. Sometimes you forget, people just bring formula out. They forget the life situation, people just grab the formula. They don't even know how to. Whereas the formula comes from the true life situation. Not that the true life situation is derived from the formula. No. The people that intelligent people that put the formula, they observe things in the true life. They have to denote it. So when you want to understand, it's good to understand from that life, not just to cram formula. I now want to go and apply it. And that's why I take the pain to explain. Now, let's look at bias theory. Okay, this bias theory, okay. Let's just quickly look at it. You understand better when we'll move further. What bias theory is just doing is just to combine the probability, the multiplication rule, and the conditional probability. How to update the probability of hypothesis when given evidence? If you simply, follow simply from the axiom of conditional probability, just conditional probability. Later, when we talk it to him, when we get to inferential statistics, we just make mention of Bayesian theory, but it's not bad, because before Bayesian theorem, this Bayesian theorem is one of the inferential method, but it's not being used now. It has been used those days, but the inferential method that is being used now is hypothesis testing and confidence interval. But the Bayesian theorem has been there even longer before those one. And that's the logic behind it. You want to test an hypothesis, provided this thing has happened. There is something that's an evidence. This hypothesis, if these have this evidence, does it prove this hypothesis? Now, look at the summary of the rules of probability. Maybe it will make you to understand the bias theory very well. Summary of the rules of probability. There's something that I will have to make mention here, but normally it's supposed to be when I get to probability distribution. But I just have to say it here. But then when I say, you understand better. Whenever you list out the possible outcome of an event, all the possible outcome of an event, all the possible outcome. Sorry, it's not event, of an experiment, rather. All the possible outcome of an experiment. It's not event. All the possible outcome of an experiment. Like tossing a die. we know that for a die is 6 possible outcomes. When you add all the possible outcomes together, they will be equal to 1. If, look at it, very simple. All the possible outcome of this, here you have all the probability of all the possible outcomes together to be equal to 1. If you look at it, there are 6 sides. Each of them, the probability of each of them 1/6. 1/6, 1/6 for all each of them 6 times, it gives you 1. For tossing a coin, possible outcome head or tail. Probability for head is half, probability for tail is half. Add together is 1. For tossing two coin, we have said the possible outcome are 4. Head, where you can call it 4 or 3. It depends on the way you look at it. If you say 3, head, tail, head, irrespective of is it the first one that is tail and head, or the first one, the second one that is tail or head. We know you have 2 head, tail there. Head, tail, head. Mean the same, 1 tail, 1 head. There are 2 of them. Then 1 head, 1 tail, make it 4. Each of them is 0.2, 1/4, 1/4, 1/4. When you add 1/4 in 4 places, it gives you 1. Probability of, if you toss 12 dice, 2 dice rather, you give 36 outcome. If you add all the probabilities, it will give you 1. So it's good to say that one, but you understand better when you get to probability distribution. The first rule per se is bound of probability, rule 1. We already said that at the section that probability cannot be less than 0, cannot be greater than 1. So it's between 0 and 1. So 0 less than or equal to probability, and probability is less than or equal to 1. That's the way to write it. Instead of writing, say probability is greater than or equal to 0 or less than or equal to 1. Just say 0 is less than or equal to probability. Probability is greater than less than or equal to 1. That means it ranges from 0 to 1 inclusive. That first sentence we say is just proved, is being put in form of a rule. The second one is what I just explained. All the probability when you have all the possible outcome, probability of all the possible outcome of an experiment or of a random variable is equal to 1. Then the additional rule for individual outcome. The probability of an event is the sum of the probability of all the individual outcome in that event. That is, if you had all the individual outcome, all the possible outcome of the event. When you can say an experiment or all the possible outcome of the event. I didn't want to use the word event, but if you want to use the word event, the probability of all the possible outcome of an event. The probability is by adding all of them together to get this one. This is what the rule 3 is saying. Now, the complement, we have already said it. The complement of probability A is 1 minus the probability A. That is, the probability of me not coming to work is 1 minus probability of me coming to work. That's just it. So that is for number 5, addition rule. Addition rule for mutually exclusive event. We have already said it before. Probably in addition rule use or probability A or B, probability, that is probability of A or B, that you are adding the A or B together is probability A plus probability B. Because there's no overlap, they are mutually exclusive. Then general addition rule is what, if you look at it, because naturally, if there is generally, if the event are not mutually exclusive, A or B will be probability A plus probability B minus their intersection. Because the intersection is counted 2 times, you remove one of it, minus probability A and B. Of course, for mutually exclusive, there's no intersection, it will be 0. That's why it's left with this one. I think it's making sense. Then probability, the rule 7, multiplication rule. For independent event, if event A and B are independent, then probability A and B is probably A multiplied by probability B. That's what we did here. Just multiply it. It gives you the intersection, what is common to them. Now, the general multiplication rule, if the events A and B are dependent now, then probability A and B will be probability A multiplied by probability A multiplied by probability B, assuming A has happened. Or you can write in this way, probability A and B is equal to probability B multiplied by probability A, assuming B has happened. So you will see something here. How, that was why I paused when I got to Bayes' theorem. You will understand the Bayes' theorem better. Why this one has two is that when you say two are dependent, A may be depending on B or B is depending on A. That is why it is written. It depends on which one depends on which. So that is why if it is A that is depending on B, so is this second one that is probability A and B will be probability B multiplied by A, assuming B has happened. This one is a conditional probability here now. So in the general rule, conditional probability is part of it. You remember conditional probability is probability. Look at this example, come to 9. For example, probability A or probability B, assuming A has happened in probability A and B, that is multiplication of this probability over probability A, which is what we saw in conditional, we are showing you in another conditional probability. So if it is B that is depending on A, you choose the first one here. If it's A that is depending on, you choose the second one. So is whichever way. That's why it's written two ways. Any of them can be dependent on one another. The conditional probability I've explained. The Bayes theory, if you look at it very well, is combination of multiplication rule and the conditional probability in testing hypothesis. Look at it. Bayes theorem B, okay. B, probability B, assuming A has happened. That is, if is my hypothesis true, like B representing my hypothesis true, probability I have this evidence A. So it will be probability B multiplied by probability A, assuming B has happened over probability A. So what is is very simple. You can just replace this one with this. So I think we should move further to quickly finish, because we will not be able to finish talk about everything today, because the topic is a probability and normal distribution. The distribution aspect will be on Thursday. Then we'll talk about different type of probability distribution and now come down to normal distribution. But to round up this session, let's quickly look at how this probability is being applied in real life. In Boolean logic, this Boolean logic is used and or not. When you want to search, maybe you are doing literature search, even on the net or whatever, or anything, you use the Boolean. Imagine somebody you are doing work on obesity and diabetes. Your work is on obesity and diabetes. If you are searching literature on the net, if you type obesity, it will give you all the work on obesity. You may not see much about diabetes unless somebody just made mention. If you type obesity, it will give you everything about obesity. You may not talk more about diabetes. Or the same thing, if you type about diabetes, you may not talk much about obesity. But since if you want both of them, you may say, okay, obesity and diabetes. This one will help you streamline your search to reduce the bulk, because it will only give you work where they did obesity and diabetes. The work that did obesity, that is on obesity and diabetes, it will give you, that will be the intersection where you see obesity and diabetes. The one that is only obesity, it will not give you. The one that is only diabetic, it will not give you. It will give you to reduce it to this. If you type or, for example, geriatric or elderly. So, you know the word geriatric, since because it means elderly also. Because if you just put geriatric, there are some words where they didn't use the word geriatric, but it's still on geriatric also. Why if you put elderly, there are some words that you are looking interested in, but because they didn't put geriatric, so you geriatric or elderly. So everything that contain, it's not only the word that contain, because if you put and geriatric and elderly, it's only in fact the study where they use the word to both of them that it will give you. So this one try to, in a situation when you want to expand, you want to capture as many as possible, you say or. If you remember our addition rule, or capture everything, and look for something that is common to the two. Now, not teenagers, not adolescent. You want the word that is only on teenager, you want to exclude adolescent. So it will give you teenager, anything adolescent will knock it out for you. So that is the way you can use this probability logic, even in real life. Okay, in data analysis, you can use it. I'm showing you some work I've analyzed using this. You know, you may say, all this probability are just talking, all this usefulness. But even when you're analyzing, if you don't have the understanding, you will not be able to capture. For example, now, if you are this issue, you want to know hypertension, who are those with hypertension. In the study, number one, the questionnaire will ask history of hypertension. Then you measure the blood pressure. No, if somebody is hypertensive, is taking his drug. When you measure the blood pressure will still be normal. It doesn't mean the person is not hypertensive. But there are some people also, the hypertensive, they don't know that they are non-hypertensive. It doesn't mean that they are not hypertensive for the fact that they don't know. Some people is systolic hypertension, but the diastolic is okay. But it doesn't mean that it's not hypertensive. Some diastolic blood pressure is the one that is high. The systolic is okay. It doesn't mean the person is not hypertensive. Can you see now what defines hypertension now? If you really want to know the prevalence of hypertension, you must be able to, and during your analysis, bring out those that have systolic hypertension based on the cutoff point of 140, and those that have diastolic hypertension based on the cutoff point of maybe 80 or 90. And now those that have history of hypertension, either the blood pressure is high or not during the time of the study. You need that logic. So it is that or and that you use, even using statistical package. For example, now, this first one, this one is about among adolescents, among students, secondary school students. So the hypertension, the measure, so there was nothing like history of hypertension among them. It was not part of the study much, but the measure, the systolic and the diastolic blood pressure. You will see that the total sample size is around 233. Out of the 233 is only about one, if you had this together that have this hypertension. The remaining, we have 310 of them that they don't have hypertension, raised blood pressure. Now, 21 had systolic hypertension. This 19 plus 2, that is 8, let's say 8. Then 7 had diastolic hypertension, but 2 had both. So that's why, if you look at it in adding a number that has systolic hypertension, 19 plus 2, 21. Number that has diastolic hypertension, 5 plus 2, 7. But number that have hypertension, either diastolic or systolic, you will accept 21 plus 7. It will have given you 28. But that one, you will have double counted the people that have both. So that is why when you just count now, 19 plus 2 plus 5, it gives you 26. That's better than hypertensive. Is this logic? So if you apply the addition rule, the A intersection B, the one that have both, has been removed. So probability of A is 21 over the total. Probability of B is 7 over the total. When you are adding, then the probability, or that is A or B, that is hypertension, will be 21 over total plus 27 over total minus 2 over total. That is, you remove it. So it has been removed here, that formula. So now look at this one. This one also is work among the adolescent also. So they talk about verbal harassment, breast caressing, unwelcome kissing, the experience some of them had. You can see the people that had, can you see, 3 issues. The people that have verbal harassment will be 39 plus 8 plus 18 plus 31. Out of the samples of 233, it's only 38 that didn't experience any of this. Those 38 are the one outside. Just like the 310 here didn't have hypertension, they are outside the box. They are within the box, they are outside those groups. So the people that are breast caressing, they are 8 plus 9 plus 18 plus 40. The people that experience unwelcome kissing, 31 plus 18 plus 40 plus 40. But if you look at intersection of people that have verbal harassment plus breast caressing is 8. Can you see? That have both is 8. The people that have verbal harassment and unwelcome kissing is 31. The people that had breast caressing and unwelcome kissing is 40. The people that had the 3 are 18. That's the way it works. I think we can stop here because the next one is probability distribution. That will be what we start on Thursday, so that you will not be, we will not suffer from information overload. Let's give room for question and answer. Question now. So you can unmute yourself. If you have questions, let me quickly go back and see if there are questions. It's only one chat I saw. Please, can you reduce emphasis on some of the basic stuff if other participants don't mind? Well, somebody asked that question, if other participants, how will I know if they don't mind? You know, the class is, you know, it's heterogeneous. But there are many, I don't just assume. So, sorry, don't worry, there's provision for, so I will discuss that today. There's provision. I know that everybody cannot be at the same page. So this is a general platform where you have to break things down. So there's provision for people that are already higher, because there are some people, some of those things are wasting their time. So there's provision which I will discuss with you. And before you ask your question, I'm very sorry, some people, I don't know those who attended the last session on Thursday, the chat after the question, after the session, I muted, I paused after the lecture. I didn't want to record the question answer session, not knowing that if I pause, I didn't record, all the chatting that comes after will not be recorded also. So some people chatted, they said I should add them to the one prof, wrote email, and one doctor put the number. I read them, but I didn't. It was when I finished and now discovered that I couldn't. I sent it to the platform that if those people, if they, I don't know, they may not even be on platform. If anybody, maybe somebody that know them, or maybe they forwarded the platform, the chat to them. Maybe I asked them to send their numbers and their email to me directly. I'm very sorry. Please, today now I decided not to force the recording. So even after the lecture, so that everything will be recorded. In the last lecture, please, what is the probability of A? If it's A, is it 90 over 28 or 90 over 26? Okay, probably.
Yeah.
Okay, ask your, okay. Somebody want to ask question? You have a question? If you have your question, ask your question. I think you have question. What's the name?
Do you have a question?
Yes. Okay, you don't have a question. The question, somebody asked question in the last.
I don't have it.
Okay. In this last lecture, please, what is the probability of A? Is it 19/28 or 19/26? Okay, the illustration I gave. Okay, if you go back, let me just go back to. Let me go back. Yes. Actually, if you look at it here, I'm not actually, if you want to calculate the probability, you now have to put the value over the total. The total, if you want to know the total now, I think the total for this one is 360, 360 or 333, 336. So this one, probability of A is 20 over total. 336. Probability of A, 21 rather, 21 over the total. While probability of B is 27 over the total. But I don't know the question you asked because let me see. The chart is not showing unless I remove this thing. I stop it. Yes. 19, okay, 19 over. So, okay. The first one is not that, you see, the probability of A, 19 plus the intersection. 19 plus 2 is 21. If you look at it, you have to look at if you want to look at probability of A, is everything inside the box A. It's 19 plus 2, which is 21 over 366, which is the total. Then the probability of B will be 7 over the total. I think I've answered the question on that person. So somebody said, please, can you send the recorded version so that we can use it to review? Okay, I will upload it because I will show you. I'll just give you the website because the issue of sending, it may be difficult to, to send. So I'll put it there. You can download it from the website. I'll give you the website. I will upload it on the website. Any other question?
Okay, sir.
Any other question? Somebody say, how do we relate this lecture to real life data? If you look at what okay, if you look at the last two slides where I talked about, okay, the last one, that's the way we relate it. Is when I gave you an example now. All those ones is using this probability that I used to generate those results. So what I did was that I will select that for this one I talk about breast caressing now. The question of breast caressing came as, did you experience breast caressing, yes or no? Did you unsolicited kissing, yes or no? This one, yes or no? So if I want to know how many people that experience unsolicited kissing and breast caressing, I would say select in my analysis in the Express or whatever software I'm using. I will select, because the way we have entered using yes or no, I will now select breast caressing, yes. And if it is if it's their intersection, that is, the people that have both, that experience both breast caressing and unsolicited kissing, I will not say breast caressing and so unsolicited kissing, yes also. Breast caressing, yes, it's got to yes, and unsolicited is got to yes. It will give me the people that have both. But if I want to have all of them together, either breast caressing or solitary, select breast caressing, yes, or I will not select unsolicited kissing, yes. So it's going to give me everything. Of course, the person that is telling that I have experienced at least one of them. That's the logic. That's the way it works in the real life. Somebody said I should repeat explanation on experiment and trial. I said the experiment is data collection. You know, just remove your mind from the experiment, from the lab that you are performing experiment. Remove your mind from experimental design, improbability. If you are asking question, I say experiment is the act of data collection. By asking question, eliciting response. That's experiment. If I ask you, you are in which profession? Maybe it's part of my this thing. I think. You say you are a doctor. I think because I already have different class of profession. I say you are a doctor. I think. I perform the experiment. You know what? By asking question and getting result. After all, when you perform experiment, you get result. My experiments that I asked you, I wanted to know your professional group, and you have given me the result. I've recorded it. That's the experiment. But if I now ask that type of question 100 times, which is my sample size, that's 100 trial. So the number of times I perform the experiment, a particular act of experiment, is the number of trial of that experiment. So you see, the number of trial now will be your sample size. While the experiment is the process of eliciting response for that variable. The funny thing is that if maybe you have a questionnaire and you have about 30 questions there, I will tell you for one person, you're going to perform the 30 experiment because each of the variable you are eliciting response, you are getting the data from, is one experiment. So for age now, by now I capture age of 400 people. My sample size is 400. For each of the 400 people, I've perform one experiment for the age by asking their age and getting the result. And there are 400 trials. For sex, it's the same 400 trial also, since I'm getting all those variables. So that's just the logic. I don't know if I've answered the person's question. Other question. Thank God for this brilliantly delivered lecture. Unfortunately, I was unable to listen to all because of poor internet network. Please, I would be most grateful if you could send your question address. I will do that. Okay, yes, Prof. I'm very sorry for not, I couldn't record your this thing then. And I now searched net, I now saw different people with your name. And all of you are prof. It's like that name carry professorship. So, in fact, I was able to get the number of one person from another center, not even your own. I called, the person did not respond. I wasn't sure if the person was actually the person I needed to contact. Thank you. I'm very sorry for that. I will send the website. Let me chat it now. Then any other question? So I will save your number and your email, sir. Let me share it's leverage. Any other question? If you can ask your question or send it as a chat. Any other question? Leverage statistics school dot. Thank you. If you have question, you can unmute yourself and ask. If you have question, unmute yourself and ask. So it's like everything is well understood. No. So I'll send out the. So I will the lecture and the voice on I will upload. You can get it. Somebody said, in what instances is research? In research, do we employ probability? Is it or? Okay, you want to ask a question? Fisayo, you have the question? Okay, somebody asked a question. He said, in what instances in research do we employ probability? Is it or? In fact, I will say or. You see, if you remember at the inception, I said probability, statistical thinking starts with probability and hence with probability. So if you look at it, by the time you understand it better when we get to inferential statistics. That is why when you want to even start your study, the issue of sample size comes. You will discover that when we talk about sample size determination, the issue of p-value, I don't want to talk about p-value because until we finish this probability, we now get to inferential statistics. That's why you understand the concept of, though the p-value say is probability, but you'll be able to understand why it is used in, in hypothesis testing. So you discover that the issue of confidence interval, which is a form of inferential statistics, inferential method also, the issue of p-value comes in, even at the section, issue of precision, even when you are calculating, and it's interwoven somehow from the beginning to the end. When you are sampling, you hear of probability sampling and non-probability sampling. Even from the inception, probability is factored in. Once you conceptualize your study design is there, be able to know the appropriate way. Study design with knowledge of probability. Those things are what guide you in knowing the appropriate sample size that will give you results that you can confidently say that this result I'm getting, which is statistics from the sample, is equal to the parameter, is speaking about the parameter in the population. I said it the last time. I said that when your statistic is an estimate of the parameter, and for the fact that you did not take you did not study the whole population, your statistic can never be equal to the parameter. So whether your statistic is now close to the parameter which you are interested in is a matter of probability. Can you see now? So the probability is is at the beginning. When you are interpreting your result, if the result, whether the result is even is valid or whatever, or is close to what you are looking for, is representative, or you can confidently say that you can generalize the result to the population. It's a matter of probability. You get to understand it better when we talk about inferential statistics. I don't know if there's any other question. So probability is needed from the conception, from time of analysis. I tell you now, if you are even analyzing, if you don't understand the logic, you will not be able to know. Somebody will just say, help me, I want to know how many people are hypertensive total. If you don't know, you won't be able to, because it's you that will tell the computer what to do. It's not the computer will not run it for you like that. It's you that give the coding. And if you don't understand, you will not know what you, or you can give the wrong thing. I will give you the wrong answer. So computer is garbage in, garbage out. So you need the knowledge. Any other one? Any other question? So I think if you want to ask question, you can mute yourself or you can type, whichever way.
Hello, sir. Can you hear me, sir?
I can hear you.
Okay, sir. Sir, please, during your lecture, you said something about calculating the probability of A, for example, when B has occurred.
Oh yes, that's conditional probability.
Yes, conditional probability. Yes, can you share more light on conditional probability, sir?
Yes, I even give example. You know,
yes.
I don't know your problem. You know, sometimes I just assume. I don't want to assume that everybody is in medical, because I try to know my audience. I try to invite as many people to benefit. May not necessarily be a health person, but a health person, when you use health language, you understand better than the person. But I usually use language that is easy for people to understand. I don't know which category you belong. But I use example medical here. I use example of diabetic and obesity. You know, many times. Okay, let's use obesity and hypertension, since people, you know, talk about, oh, obesity is a risk factor for hypertension, right? So if you are studying, in your study, you want to know, okay, you want to know how many of these people that are obese in this my study have high blood pressure. So you may say, okay, among these obese people, I want to know the prevalence. You know, you can know the prevalence of hypertension generally. But you may not say, okay, among these people that are obese, what proportion are hypertensive? You want to see if it's even greater than the total proportion that is hypertensive among the general. That's a conditional problem. You know, when you do it, you're going to say, oh, 50% of the 50% of the people that are obese are probably hypertensive. Is it no probability? 50% means 0.5. What he just did is to say, okay, if out of maybe 400 people you study, 50 are obese, and out of the 50 that are obese, 20 are hypertensive, 20 over 50, that's 40, 0.4. So the probability of obesity, of hypertension among the obese is 0. So it's conditional probability. Probability that somebody is hypertensive, provided the person is obese. That is conditional probability. Can you see? People that are asking how it is used in the real life, that's an example.
Okay, sir.
It's a conditional probability. So if you look at it, who are those people? What will form your numerator? Let me just go. I will show you something. Let me go to that slide, because this slide I talk about, this is the one, right? Now, this is conditional probability. So who are those people? I want you to respond. Who are those people that will form the numerator? If you want to calculate probability, you want to put people that are hypertensive among the obese. Who are those people in your study that will form the numerator, the upper part? I want you to respond. I don't know. You will
Okay.
not.
Okay, the question, sir.
Who are, you know, if you want to calculate the probability, you want to say, you want to know what proportion of people that are obese that are now hypertensive. Yes, I mean, I say that's an example of conditional probability. You're going to put, okay, you're going to divide people that are obese in the hypertensive over the people that are obese. Is that not so?
Yes.
Yes, but if you look at it, they are the people that are obese and hypertensive. That is the if your A probability of A is probability of being hypertensive, and your probability of B is be obese, and you are not saying the probability of A condition to B, that is, provided the B has happened, probability of hypertension provided the person is obese, that's what it means. So you're going to see that the people that form your numerator will be the people that are obese and are hypertensive. Is that also? That is the intersection of A and B.
Intersection.
Do you get it now? And the people that will form your numerator will be the people that are obese. That is the blue. Does it make sense?
Yes, sir.
So the issue now is, sometimes that's why my lecture I want you to learn statistics without being bogged down with equation. We just need the equation to explain. Either a lot of people are going to even more complex, we may not even use the equation, it's just logic. You see, we will not use the equation because the equation should not actually replace the equation, should not, it's just to debug so that the expert, the intelligent people, the expert over the years, instead of saying this in word, so that it won't be too wordy, they now put formula, draw diagram to denote it. But sometimes if you don't understand, some people, the even diagram will even confuse them. I'm trying to interpret it to you now. You see example of computational probability now. So I think you understand that now.
Yes, sir. Thank you very much, sir.
Welcome.
Yes, sir. It's clear.
Please, which one is dependent and which one is independent factor out of the obese and hypertension? Okay. Now, even from what we even said now, you can see that the dependent factor is the hypertension that depend on obesity. Yes, I know. That's why we say, what is the probability of hypertension if obesity has happened? So the obesity, the hypertension depend on obesity. Obesity is independent, hypertension is dependent. That is the belief we have acquired over years. You know, when you are, you know, we are not discussing study design. In study design, in descriptive study, in cross-sectional descriptive study, cross-sectional study, one of the drawback or major drawback of cross-sectional study is you cannot establish temporal sequence. That you cannot say the exposure comes before the outcome. Imagine if you are studying people now, you are studying obesity and hypertension, you just use cross-sectional study, where you just go once and you take data, you measure blood pressure, you measure weight, you measure height, all those, you calculate your BMI and say these people are obese, these people are not obese. You measure the blood pressure, you say, you now say these people are hypertensive or not. You now realize, it's like more of these obese people are hypertensive, but forget that some of them that they were when they became hypertensive, they were not obese. It was after they had become hypertensive, they became obese. So in your study, you could not establish that obesity for all of them, obesity, you cannot even establish for anybody that obesity started before hypertension. There's no temporal sequence. But in other study, case control, cohort study, experimental design, you can establish that. Because you can actually, this one, you can actually establish the fact that this thing come before you actually establish the fact that the exposure come before the outcome. let's just assume that in this situation now, we are saying that obesity came before hypertension. So the dependent variable is hypertension, the independent variable is obesity. Any other one? Any other question? Yes, Ganiyu. Say your question. Is it that you are clapping or you are raising hand?
Clapping for you, sir.
Okay, thank you. I'm clapping for you also. Anyway, any other question? We have 11 people remaining. Okay, if we don't have question, maybe we can close the meeting. So I think everybody has seen the, you can visit the website. So for the person, I don't know the person that raised the concern about somebody asked another question. Sir, using this example of obesity and hypertension, what will be the general probability of hypertension among the obese? Is A over A plus B. You know, if you remember the general addition rule, obesity and hypertension, they are not mutually exclusive. Are they? No. For the fact that somebody is obese doesn't mean that someone cannot, so they overlap. So the general equation now will not be probability A or B will be probability A plus probability B minus probability A and B. That would be the general probability, the general equation for addition. If it is multiplication, no, multiplication is going to be probability A and B. You go to probability A multiplied by a probability B multiplied by probability A. Assume B has happened. Can you see? If you want to use conditional something, just like the one I explained now, conditional probability rule, it's going to be probability A is probability AB, A is probability A times probability B, A has happened over probability A. You can just use, you can use either the, you can apply any other rule. It depends on what you are looking for. You can apply the addition rule. It's the general addition rule that we apply now because they are not mutually exclusive. Sorry, they are not mutually exclusive. They overlap. The general addition rule. The multiplication rule also will apply. It's the general multiplication because they are dependent. They are not independent. They are dependent. General multiplication rule apply. And the conditional probability rule apply. Bayesian theorem apply. Can you see? Those are the formula that apply there, depending on what you are looking for. Any other one? You see, the probability is not dry. It's because you just need to understand the concept. You use it everywhere. We talk about Boolean. Even Boolean logic, Boolean was a German that invented this in long ago. I don't even know that, but I don't think the probability had advanced by that time when he invented the Boolean logic using and, or, and not. And it's the same thing we use in analysis, in searching on the web, whatever you want to do. So you just need to understand it. When you understand, you can use it in every walk of life, not only in that analysis. Even interpreting is all many things you can do. So yes, the question, the person that was talking about that I should know, if other people will not mind, I should not emphasize some other thing. One of the major problems, if let's say it's a physical classroom, I'll be able to ask if you understand. But in this case, if you do that, you will begin to make noise because at the inception, the beginning of the series, we allow people to know to be unmuted, but people were just making noise. If let's say in the process, somebody can just say, okay, we understand, then we can just proceed. But I first of all deliver the lecture to the best of my ability so that as many people will understand as possible. So before I entertain question, that's why I try to break it down to the first principle. So on the website now, you're going to see my training. Some are free, some are not free, in the sense that they are, for you to understand something also, you need more focused training. The focused training now, I will try to do it because I know that this COVID-19 will soon go. People will still be going for work, or they may not have all the time. So we'll use weekend. That's what I've been doing for my training before. They will use online, weekend. So 10 hours, 5 hours, and maybe 2.5 hours on Friday, 5 hours on Saturday, then morning, 2.5 hours in the morning, 2 hours in the afternoon or evening on Saturday, 2.5 hours in the evening on Sunday, making 10 hours. We focus on some things like SPSS, use of SPSS, maybe ANOVA, logistic regression, linear regression, logistic regression. So, and once you come, you want to know the nitty-gritty. When we run it also, how you can run it with SPSS, we'll look at the result, we interpret the result. So focus training. So very soon you'll see I wouldn't know if anything can be done this weekend, but start upper weekend. I will post it to, you can visit the website there, I will post it to the WhatsApp group. So maybe we can even start with maybe the statistics using SPSS. Why I choose SPSS? SPSS is the easiest package to learn statistics. You may learn other things like stata, like people in academics. The academic is going towards stata. The SPSS is more business and it's easier. It has the best graphical user interface. You can easily teach people who easily know, especially doing this online now. Press this, press this, press this, press it. You put the module, you have the module. I just give instruction, you do it, you get the result. So at this modern age, there's no point saying I'm giving you something to solve with hand. Even though in the module you see the example with hand which I solved it. In the real life, you use computer. How do you use computer to do this thing? And that is where the world is going. So that's what we're going to be doing on the focus training. The focus training, the first one will be the use of the SPSS, how to do many things with SPSS. Then particular analysis now, some of the ANOVA. 1 weekend, just put something you can finish in 1 weekend. Because sometimes if you don't put it together like that, you forget. And once you put it together, you start using it, don't stop using it. Just lay your hand on some things and your home and dry. And if you continue practicing, you become better and better. Kindly help us with audio record via yahoo.com. Then I will send it to, I will not send because it's going to be difficult uploading, attaching. It's going to be heavy. So you get it on the, I'll upload it on the website. I'll put the website. Visit the website, you can upload, I will upload this session. It's a pity that, anyway, no, I don't know, because I will have paused the other time. I didn't want to make mistake. I think if I pause now, any particular, maybe I should even pause and start recording again. Because normally I want to debug the session so that it will not be too heavy, so that in trying to download it, you'll be able to download. So this question and answer session will not be there. But I did that the last time. I lost. So I lost all the chatting, and I could not respond to the chat because I didn't save them. So any other question? If there are no question, I think we can stop for today. Thank you, everybody.
Thank you very much, sir.
Welcome. Go now.
Yeah, thank you, sir.
Thank you so much, sir.
Thank you.